Okay, hello, everybody. My name is Keon, and I'm here going to rank the theorems that I've learned when I took abstract algebra this past semester. So I have a list of the theorems here. I kind of went through the book, picked out the ones I think would be interesting to rank, and I'm just going to rank them, okay? Because there's a lot of cool stuff here, you know. This is definitely not comprehensive. This is just a sampling of what I learned in my course, right? So we did a bit of like group theory. We covered some rings and some stuff about fields, but we didn't do everything. So this is just like a nice sampling of theorems here. But yeah, this is going to be fun. There's a lot of cool stuff. So let's just get started. What I'm thinking of in like terms of how I'm ranking it, I'm going to rank it based on like how cool the theorem is. I mean, that's a big thing. Sorry, let me silence my phone. I'm gonna rank it on how cool the theorem is, mixed in with how useful it is, because that's also obviously important. And so yeah, we'll just rank it like that. So I'm just gonna double check if I'm recording. Okay, everything's recording. Cool, cool. Let's just get started. Okay. So this first theorem here, I also did it in chronological order, in case I didn't say that. So we're starting in like the early stuff about integers, basic kind of stuff. But this first one, theorem 1.1.6, it's talking about how you can represent, if you have two integers and you're considering the greatest common divisor of the two integers, you can write that greatest common divisor as a linear combination of the two integers. So, you know, obviously it's not that exciting of a result. But with that being said, it is useful. It's used to prove other things from what I've seen. So, it's not the best thing in the world, but it's kind of cool. It's kind of useful. So we'll put it in B tier for now. Put it in B tier. All right. So what about the next one? This is Euclid's lemma. Okay, so it has a name. So it's an important one. So this one's talking about prime numbers, and if it's saying how if the prime it's like a characterization of prime numbers. So if P divides AB, then either P divides A or P divides B. Now, see, that one's pretty cool. It's kind of short, it's kind of sweet. At first, when I saw it, you know, I was like kind of confused. I was like, why does that mean it's prime? But then I realized, oh, because prime numbers, you know, it's impossible to find smaller factors that multiply into the prime number. So of course, if the prime divides a product, it needs to divide the individual elements, right? So it was kind of interesting when I got the intuition. And there's also parallels with other things. Like there's a similar type of result for polynomials. So it's a cool one, but it's also not like amazing. It's not mind blowing either. So I'm just gonna put it in a B tier as well, maybe above the other one. Also, I just realized this video is gonna be forever because I put a lot of theorems here, but that's okay. It's gonna be fun. It's gonna be fun. Okay, so this next one here, fundamental theorem of arithmetic. That's basically how you can, given any integer, you can factorize it in terms of like a product of prime numbers to like raise to some exponent. So it's kind of like a factorization theorem for all integers. So like this one's kind of like, again, it's not mind blowing here, but it's useful. It's a useful result because it's like anytime you have an integer, you know that boom, you can just factorize it in this way. So it's used in other results. So I'll put it again in B tier, nothing fantastic, but I think the prime one's cooler, so I'll put it in between. Yeah, that's good. Okay, let's see this next one here. Euler's theorem. It has another name. That's pretty cool. So this is honestly, I kind of forget this one. This one's kind of, I don't know. It's like whatever. It's some congruence. If a is relatively prime to n, then a to the power of this Euler totient function thing. It's congruent to 1 mod n. I don't know. That one's a bit boring to me. That one goes in C tier. I mean, it was kind of interesting, but like it's not really used in the class that I took that much, so it's like it's kind of just whatever. And the same thing with this next one. This is Fermat's little theorem or something like that. It's talking about if p is a prime number, then for any integer a, we have a to the p is congruent to a mod p. That one's also a C tier. I mean, that's just kind of like, it's like whatever, you know? It's not that crazy. Hey, but this one next, this is Euclid's theorem. There exist infinitely many prime numbers. That one's kind of cool. Because it's kind of a bold statement, you know what I mean? It's like infinitely many prime numbers. It's like, how do you prove that? Well, yeah, that was pretty cool. You know, it's not really useful in the course that I took, but it's kind of neat. So I'm gonna put it in C tier as well, but I'll put it ahead of the other ones because it's kind of it's a cooler statement. You know what I mean? All right, let's look at the next one here. Okay, this next one's talking about equivalence relations, and I actually really like this result. I like this result because it's really important for so much of the rest of the stuff you learn in abstract algebra. It's basically talking about how an equivalence relation on a set partitions the set. And conversely, any partition on a set determines a equivalence relation. And that's a really important kind of theorem because it's used, like I said, it's used to equivalence relations in general are used everywhere in abstract algebra. You know, it's used to define quotient groups and other kind of quotient objects like that. And this idea of it partitioning the set is an important idea. So I found that, and I found it also kind of interesting when I first learned about it as well. So you know what? That one's going to be an A tier. I like that one. That one gets an A tier from me. Cool. Okay, so this next one, we're finally getting into some stuff about groups. You know, groups, the first kind of um, algebraic structure you learn about. And this one's kind of just a basic, it's not really a crazy theorem. It's just talking about orders of an element. So it's saying how, like, okay, if an element of the group G has infinite order, then a to the power of k is not going to be equal to a to the power of m for any integer. And some other stuff about how, you know, some other resultant orders, like for example, if you take the cyclic subgroup of A, the cyclic subgroup generated by A, then the order of that subgroup is equal to the order of A. So that's actually a useful result. So this is actually kind of a useful thing because a lot of the times when you prove stuff when you prove stuff about groups, you're using stuff about orders. So that's kind of it's kind of an important thing. So that gets a you know, where should we put that? Like an A? Yeah, an A. Okay, that gets an A. Sure, gets an A. That one's pretty good. Okay, but this next one though, Lagrange's theorem, come on. That's a cool one. See, anybody who knows group theory, you know Lagrange's theorem is like quintessential, okay? The fact that if you have a subgroup of a finite group G, then the order of H divides the order of G. That one's a crazy result, you know, because it's like on one hand, you know, it's like it's easy to understand, you know, it's easy to understand if you have a subgroup of your bigger group, then the number of elements that are in the subgroup divides the number of elements are in the bigger group. I mean, come on, it's a good theorem. It's used to prove so many other things. So ladies and gentlemen, that is our first S rank. Okay, that is our first S rank. Good stuff. Okay, this next one, this one's small. I can barely even read it. um it's talking about more stuff on like orders of elements. It's talking about yeah, like if you have a finite group of order n, then the order of any individual element divides the order of the entire group. So I mean, it's not a really interesting result, but it's also useful. It's a useful kind of thing. So I'm also going to put that in A tier just because it's useful. You know, when you're doing things in group theory, you're talking about orders of elements all the time. So it's you know, okay, my camera just cut out, so we'll just restart that. let's just double check. Yeah, okay, that's good. That's good. Everything's good. Okay. Okay, this next result. I mean, this is the first one that when I saw it, I was like, damn, that shit's cool. Any group of prime order is cyclic. Now, of course, that's going to be S rank material right there. And it's so cool because for a few reasons, right? You're kind of it's like a characterization of all groups that have a prime number of elements. So right there, that's kind of cool, you know? You have a statement that's just like characterizing, like give me a group, of 7 elements. This theorem says that that group is going to be a cyclic group. Give me a group of what else is prime? I don't know, give me another prime number. 5 elements. That's also going to be cyclic. You know what I mean? It's like it's kind of cool because it's just like it's a very general result. And also the thing I like about it is that the proof is actually kind of simple. It's only an application of Lagrange's theorem. So it's kind of a nice thing, it's not a complicated idea, but it's a cool idea. It's a cool idea, but not complicated. It's also useful. So I like that. I like that. All right, let's see what's up next. Okay, we're talking about some things about isomorphism, some results about isomorphism between groups. For example, if A has order n in G1, then phi of A has the same order in the other group that you're constructing the isomorphism between. That one's pretty useful. Um, yeah, that one's pretty useful. I mean, it's not that interesting, but these are useful results as well. So this one is going to go. I'll put it in I'll put it in B tier because it's kind of obvious. It's not really like it's kind of an obvious result almost, but it's useful, so we'll do that. Um, okay, what's next? Okay, some stuff about cyclic groups. Every subgroup of a cyclic group is cyclic. That one is that one's all right. That one's all right. I do enjoy the stuff regarding cyclic groups because they're so easily understood, right? So the one that's coming up next, after this one that we're on right now, that one's a cool theorem. But this one, the fact that every subgroup of a cyclic group is cyclic, I don't know. That one doesn't really impress me that much. That one's just kind of like whatever. Like it's useful, but it's kind of like whatever. So that one gets a C tier. But this next one though, if you have a cyclic group, you automatically know that it's either isomorphic to integers or the integers mod n. That one's pretty cool, because it's like the group of prime order being cyclic. The fact that you're kind of having a statement that is characterizing a whole class of objects, stuff like that is really interesting to me, and it's really fun. So I like this one. Yeah, because basically, anytime you have a cyclic group, all you need to be thinking about is the group of integers or the group of integers mod n. So that's a cool result. Easy S rank, but below the other S ranks. Yeah. All right. This next one. This is another big theorem in group theory, Cayley's theorem. So it has a name. So when it has a name, it's a big deal. Um, the fact that every group is isomorphic to a permutation group. This one's kind of cool as well. I'm gonna give this one an A rank. I'll give it like the highest tier of A rank. It's not gonna get an S rank. It gets an A rank because it's a cool theorem. It's definitely cool. It's another again, just like the stuff on cyclic groups and just like groups of prime order being cyclic. I really enjoy those statements that um, are very general because those are kind of interesting results when you have a very general kind of thing. But the fact that every group is isomorphic to a permutation group, it's not like from what I've seen so far, it hasn't been very useful um, in abstract algebra. It's kind of just like an interesting idea, but it's not the most useful. So it's cool, but it's only gonna get an A rank. Okay, okay. This next one is kind of cool. It's kind of hard to read, but It's basically the connection of if you have a homomorphism out of your group G, then it basically says that the types of homomorphisms you're allowed to construct out of a group is basically found within the normal subgroups of the group. And that's kind of an interesting idea. It's still an idea that I haven't fully grasped yet. I'm still a beginner at this stuff, so I haven't learned it completely properly yet. But it's a cool idea. So I'm gonna put this in B tier. Actually, no, it gets an A. Gets an A. 'Cause it's an important idea. Um, yeah, basically, if you know group theory, it's the fact that um, kernels are normal subgroups and normal subgroups are kernels. It's basically that thing. So obviously, that's an important idea. So it should get a good A tier there. Okay, but this next one, I don't even have to say anything. This one gets top tier S rank, the fundamental homomorphism theorem. Anyone who studies abstract algebra, this one is used everywhere. It's the fact that if you have a homomorphism between two groups, there basically exists an isomorphism within that homomorphism. It's such an interesting result to me. It's one of those things where when you first look at it, you're like, what the hell is going on? But then when you finally understand it, you're like, oh, that makes a lot of sense. So it's cool and it's used all over abstract algebra. So it's some good stuff. That gets the highest rank, highest S rank. All right, so next up, all right, we got a few more here. This is a long video. This is longer than I thought it would be. Um, but this next one's about polynomials. This is when we kind of move towards learning about polynomials in the course. So this one's talking about how a polynomial of degree n with coefficients in some arbitrary field has at most n distinct roots in f. So, okay, that one's okay. That one's pretty good. It's a useful result. Of course, it's useful. Also not very mind-blowing, so I'll just put it in B tier. Useful but not mind-blowing. This one I like a bit more. It's a similar kind of result about polynomials, but this one's talking about how if your polynomial is degree 2 or 3, then it's irreducible over the field, if and only if it has no roots over the field. So this is a useful result. I like it because it's not complicated. It makes perfect sense why it's true. And it's also very useful when you're working with polynomials. So this one gets an A rank. I'll put it low A rank though. Okay, this next one about polynomials, I definitely enjoy this one. Sorry, my camera kind of cut out again there. Anyway, where was I? I was talking about Kroneker's theorem. Yeah. Okay, so this one's pretty cool. This one's pretty cool. It's the one, it's basically talking about if you have a polynomial over a arbitrary field, then what the theorem says is that there always exists a bigger field such that that polynomial has a root in the extension field, in the bigger field. So that one's kind of neat because it's just like, I kind of like the idea. It's like, okay, you have a polynomial over some field and you want to see if it has roots, and let's say it doesn't have any roots, so it's like irreducible over that field, then it's just like, just make a bigger field, Just make a bigger field and it'll have a root in that field. If you make the extension field in a certain way, it'll have a root in that extension field. So that is kind of cool. I like that idea. It's fun. It's useful. So that gets an S rank. That gets an S rank. We'll put it up in the S tier. Okay. All right, we got a few more left. You got a few more left. This is a hefty tier list right here. Very hefty. Okay. So this next one, fundamental theorem of algebra. This is a classic. The fact that any polynomial of positive degree with complex coefficients has a complex root. That one's good. It's one that if you've studied math, you've definitely heard of before. It's not really something unique to abstract algebra. Like you've learned it in different classes. And it's a cool one, but it's also not really used much in the course that I took. So I'll just put that as a B tier. It's kind of cool, but it's like it's like whatever, it's whatever. Okay, so these next two are about this is about rings and fields now. So this is the kind of the last section of the course that I took. It did some stuff on rings and fields, and that's about it. So these next two theorems are kind of similar to each other. It's about integral domains and fields, basically. So the first one is the fact that any subring of a field is an integral domain. And the second one is any finite integral domain must be a field. So out of these two, I definitely like the second one better. The fact that any finite integral domain must be a field, because that one's a little bit less obvious, maybe. Because this first one, the fact that a subring of a field is an integral domain, that one's like a little bit. It makes sense. You don't have to think too hard about it. Still cool. I'll give it an. I'm gonna give it an A rank just because I like fields and integral domains. They're kind of neat. But the second one, the fact that any finite integral domain must be a field, that one gets a higher A. That one gets a higher A. 'Cause it's a little bit less obvious to me, So yeah. Okay. All right, we're almost done here. We got a few left. Let's finish this tier list off. Okay, let's see. This next one here, it's saying how an integral domain has characteristic 0 or p for some prime number p. This one I like. This one I like. I'm actually going to give this one an S rank if I can scroll up here. I'm going to give this one an S rank for a few reasons. The first one is that it's not really obvious to me why an integral domain has characteristic 0, of course, it could have characteristic 0. But the fact that it has characteristic p for a prime number, that one's kind of cool. Like it wasn't obvious to me. And the theorem also used the fundamental homomorphism theorem, which I liked. And it's just kind of a neat theorem. So I liked it. Yeah, I like the proof. I think it's interesting. Yeah, so it was cool. All right, this next one here. Right, this one's good. This one's useful. It's saying basically, if you have a field, then automatically it has no proper non-trivial ideals. And that's an if and only if statement as well. This one's kind of cool as well. I'm going to give it an A rank. I'll give it a low A rank. Um, this one's nice because it's like, it's another one of those useful results because obviously in ring theory, ideals are an important concept. And so if you have some sort of characterization about the kinds of ideals fields could have, then it's a useful kind of result, and it's used in other places in ring theory. So that's nice. That's nice. Okay, so these last ones here, I don't know. I feel like I'm a little bit less familiar with it because the ring theory stuff in the course was, we didn't cover it too deeply, so I'm not as familiar with it. But I do kind of like this result. This one's talking about factor rings and basically when a factor ring is going to be a field and when a factor ring is an integral domain. And it's basically, if I is a maximal ideal, then the factor ring modulo I is going to be a field. And then if it's a prime ideal, it'll be an integral domain. It's a useful result. It's used for like other proofs from what I've seen. So I like it. I'll put an A rank. If you can't notice, I'm getting kind of tired right now. That's why I'm trying to go faster here. It's tiring talking for 20 minutes. I did not realize. But anyway, this is like my first video, so whatever. Um, okay, three left. Let's get through this. Three left. What is this next one? Each non-zero prime ideal of a principal ideal domain is maximal. Okay, prime ideals are maximal in principal ideal domains. So from the last theorem stated that maximal ideals are prime. And now this is saying that prime ideals are maximal if you're in a principal ideal domain. So that's a nice result, you know. It's a nice result. Since I'm less familiar with ring theory, um, I don't like totally know all the areas and where this result is used. Oh, it's probably used for polynomials and talking about uh, when factor rings of polynomial rings, when that's going to be a field. And it's probably if you have an irreducible polynomial and you're considering the principal ideal of that irreducible polynomial, it's probably going to be a prime ideal. And therefore, since the polynomial ring is a principal ideal domain, that prime ideal is going to be maximal. Therefore, the factor ring will be a field based on the last proposition there. So anyway, yeah, that was just me just figuring it out as I'm going along. But anyway, I like these ideas of prime ideals, maximal ideals. They're pretty cool. So that gets A ranks. Okay, these last two theorems, they're basically regarding the last thing we learned in the course. Um, it's about quotient fields. This is pretty cool. I like the idea of quotient fields. It was basically like, you know, when you have an integral domain and you're trying to consider, you know, can you make a field out of that integral domain? Because, of course, if you know ring theory, integral domains have the cancellation law, but they don't necessarily have inverses for each element. So basically, the quotient field idea is basically trying to create the idea of fractions for the elements of the integral domain. So you're kind of like extending it in order to be a field by kind of creating fractions. So it's a cool idea. So this theorem right here is talking about how if you have an integral domain, then there exists a field that has a subring isomorphic to D, which is basically saying if you have an integral domain, you can create some sort of bigger field that is extending the integral domain to have inverses for each element. So it's a cool idea. I like it. I like it a lot. I'm gonna give it S rank because I just kind of find it to be a neat idea. And then finally, ooh, this is a long video, man. A long video. Finally, this is also having to do with quotient fields. It says that any field contains a subfield isomorphic to the rational numbers or integer mod p for some prime number p. Now, since I'm so tired, I don't really feel like talking about this one. This one gets an A rank. It basically has to do with that quotient field idea. Sorry, I think it cut out a little bit there. Yeah, anyway, where did I put that one? I put that in A tier. Okay, the last theorem, the one that says any field contains a subfield isomorphic to Q or ZP, that one's a nice A tier because you know, I thought it was a little bit unintuitive at first, but it's a kind of an interesting result, you know, the fact that you have the rational numbers hidden in the field somehow. It's nice. So yeah. Man, okay, that was way more tiring than I thought, but there you go. That was my ranking of the theorems I learned in abstract algebra. So maybe I'll make more videos about math and other things. We'll see. But yeah, thanks for watching. Have a good one.